Sorry? People shaking their heads no. This is it now. Now is it. Excellent. You important people are around. Catchin, you're the official videographer? Yeah. All right. Give people just a minute to settle, and then we will start. You're going to do PAC Learning as we discussed. Great. This one person will be happy. See about the rest of you. All right, you ready, Catchin?
Yeah, ready.
All right, we shall go then. So let's see. Your beloved Virgil is not here today. I'm sure he told you this. So my name is Jay Aslam. So I am a professor here. I'm sure you've seen me floating around the building. I also happen to be Virgil's PhD advisor. So I guess if he's your professor, I'm your grant professor or something. Kind of scary, actually, to think of it that way. So he asked if I could come in and fill in for him today since he's out of town, which I'm happy to do. What I want to do today is, it's like Monty Python said right now, for something completely different. So let's think about what you guys have actually done over the course of the term so far, right? So you've actually learned a lot of different machine learning techniques, right? So you've done, I presume, things like linear regression, logistic regression, support vector machines, neural networks, perceptrons, gradient boosting, et cetera, right? So you've done a lot of machine learning. And I'm sure you've run a lot of experiments on data, right? At least that's the way the class was when I taught it last. And I'm sure you've learned some principles over that course of time. Things like, if I want to learn better, I need more data. If the thing that I'm trying to learn is quite complex, then I have to have, a complex classifier. A linear classifier is not going to cut it for something which is nonlinear, et cetera, et cetera. And now the question is, well, can we actually quantify any of that stuff? So like, for instance, when you say that I need more data if I want to learn better, well, how much more data? If I want to learn at a certain level, how much data do I really need, right? How do I measure the inherent complexity of the class that I'm trying to solve, and how does that factor into the amount of data that I need to be able to solve it? Even bigger questions. Are there things which are fundamentally unlearnable, and why? Are there things which are fundamentally not learnable efficiently, and why? And so on. And so, these sorts of questions have arisen. I'm sure they arise in all aspects of science. You can go to physics, and people develop all kinds of formulas for modeling the world, and then eventually you want your grand unified field theory. And this sort of thing happens in computer science as well, right? So let me just take a couple of simple examples. So for instance, I presume you've all taken a course in algorithms at some point in time. You've learned lots of different sorting routines. You have insertion sort, runs in n squared time. You have, shell sort, runs in like n log n root n time or something like this. Then you get to something like, merge sort, n log n time. Can you do any faster than that? The answer is no, right? So, and how do you prove that it's not? Well, you have to essentially build a model, essentially for what the sorting problem is. In this case, there's something called the comparison tree sorting model. And then within that model, that mathematical abstraction of what the sorting problem is, you can actually prove that you need n log n comparisons to sort. And so as a consequence, things like merge sort are actually asymptotic algebra. The same sort of thing happens at the whole level of computation, right? What is our mathematical abstraction for what computation is? Turing machines, right? So, are Turing machines interesting devices in and of themselves? No, not particularly. We don't actually build Turing machines, although people have. But they are extremely interesting mathematical abstraction for what it means to do computation. And then if you can prove, it's very hard to prove something about what one of these things does, okay? But if you can essentially argue that what this thing is capable of is equivalent in terms of what a Turing machine can do, and then you can prove something about this mathematical abstraction, Turing machine, then you actually say something about these real devices that we use. But you need this mathematical abstraction, right? And so once you have Turing machines, you can prove things like, that certain problems that we've been banging our heads against for a long time are just completely intractable, like the halting problem. Problems that we've tried to find efficient solutions for, but have never been able to do so, are likely to have no efficient solutions. Things like the traffic salesman problem. This is the province of computability theory and complexity theory. But all of those things are enabled because you have this mathematical abstraction that then you can prove something about. So, having said all that 5-minute prologue or monologue or whatever it was, both. The goal for today, essentially, is to give you that mathematical abstraction of what machine learning is. Okay? So we're going to give you the equivalent of, a Turing machine or a model for what the learning process is. And within that model, we can then make very concrete all of these questions that I posed at the very beginning of this lecture. Very concretely, I can show you, if you want to learn better and better, you will require more and more data, and here's how. If your problem becomes more and more complex, you will need more and more data and a more and more complex classifier to learn it, and here's precisely how. Here is the right measure for measuring the complexity of the task that you're trying to solve, so on and so forth. So we'll actually do all of that. And so this all came about for much the same reason that things like the Turing machines came about, or the circuit complexity models, or the comparison tree models for sorting, is that eventually, people in our field, my field, machine learning, they have been hacking away at machine learning algorithms for decades, right? So I came of age doing machine learning in the late 80s, early 90s. And so we had lots of machine learning algorithms at that point in time, not all the ones we have today, but we had lots. And eventually people started asking the question, well, some things seem to be hard to learn. Why is that? Some things seem to require lots of data. Why is that? And then eventually somebody came along, ended up being a guy named Les Valiant over at Harvard, and he developed something called the PAC model of learning, which is sort of the equivalent of the Turing machine, but for the machine learning process. So what I want to do today is really describe what PAC learning is, how it's a model for machine learning, and then give you some of the important and basic results in PAC learning. Sort of the equivalent of if you were studying computational complexity, I want to teach you what is NP completeness, and then to show you that a bunch of different problems are NP complete, and then to show you a bunch of different problems that you can actually solve in polynomial time. I want to do all of those things today, but again, with respect to machine learning. Okay? Does that make sense? Okay. So we'll do this. So PAC learning, obviously this is all capitals, that's an acronym. This stands for something called probably approximately correct, but that'll become abundantly clear when I actually go through what is going to be a really long definition of what PAC learning is. So let me do the following. This is sort of the structure of today's lecture. I want to define what PAC learning is carefully so you understand what this model is. This is sort of teaching you the equivalent of what a Turing machine is, but this is not for learning. I then want to show you that, that within this model we can actually learn things. Okay? I also want to show you that we can prove some very, very general theorems about how much data is required and what is the fundamental correct measure of complexity of a learning task. So we'll see all of those things today. And also I want to show you both upper bounds and lower bounds. I want to show you that here's actual algorithms for solving machine learning tasks, and then here are lower bounds on data requirements you are just going to absolutely have to meet if you hope to be able to learn and learn well. And that'll sort of end today's lecture. And if we have a little bit of time at the end, I might talk about more things like noise tolerance and other things. But this model is very generalizable to lots of different things. Okay? But just to give you a sense of what's learnable and why, and at what level of efficiency. Okay? Now, to get there, I'm going to have to do a little bit of dry stuff in the beginning. We have to set up this model. It's going to take a while for us to sort of give you what are all the pieces and components, and the actual definition of PAC learning is rather lengthy. But then once we have that, I think it's reasonably intuitive, and then we can move on to do the more interesting things about actually building some PAC learning algorithms and then talking about the other things. Okay? All right. So here is the basic components for PAC learning. Okay? The pieces that we're going to need. It's going to take me a board to write down pieces, and I'll have one board dedicated to this definition. Okay, of what PAC learning really is. Okay? So the idea for PAC learning is, let me start with an example, which I'll use as an example to begin with, and then it'll make it easier to understand all the mathematical notation. So I'll use as an example one that I oftentimes use when I teach this class, and that is, suppose that my task was, I'm working in a hospital setting and somebody wants me to build a predictor for whether somebody has the flu or not. patients walk in the door in the emergency room. You know, you take a bunch of different measurements about them. You know, you take their temperature. You know, you're asking about their symptoms, so on and so forth. And you'd like to have a rule which classifies well whether they have the flu. Okay, and the things that you might ask about the patient can have all these are features essentially in machine learning context. You're extracting features from the patient, right? I don't take a patient and throw them into a tool. I extract features from the patient and throw that into a tool, right? And so the features you can extract are going to be things like, you know, what is your temperature, what is your age, what is your sex, you know, what are your symptoms, are you having chills, so on and so forth, all the sorts of things that you're normally asked when you're sick and you go to the doctor. For the purposes of today, I'll assume that for simplicity, this is not required for PAC Learning, for this running example, I'll assume that these are all binary features. Okay, so you're either male or female, you have the chills or you don't have the chills, your temperature is high or it's not high, so you know, whatever, there's some threshold, so on and so forth. So let's assume for the moment that they're all binary features. Okay, and so essentially every single person just gets turned into a feature vector, the sorts of things that you've been using all along in this course. Okay? So I'm going to view that as all possible feature vectors that I will ever see, the universe of them, is going to be an instance space. Okay? This will be X. This is my instance space. And you know, if I have all binary features and I extract n of them, then your instance space would be, you know, 0, 1 to the n. It's a bit string of length n. You know, you're male or you're not, your chills or not, your high temperature or not, blah, 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 and different features that I've extracted, all of which are binary. Okay? For the moment. It's not required by PAC Learning, but for the purpose of this thing. Okay? So that's the first thing. The second thing is I'm going to assume that there's a certain concept that I'm trying to learn. Okay? And that concept is going to be essentially a subset of the instance space. In other words, these are all the people that have the flu, and these are all the people that don't, right? And essentially what I'm trying to do is I'm trying to correctly predict whether you're in that class or you're not in that class, okay? So there's going to be some concept C, which is an element of some big concept class C. This is the thing that I'm trying to learn. This is the class I'm trying to learn. Now, my assumption, and this is the standard machine learning assumption, is that this class that I'm trying to learn has structure, right? If it doesn't have structure, and we're going to have to define what structure means later, right, then it's going to be impossible to learn it, right? If the thing that I'm trying to learn is sort of a randomly chosen subset of this thing, there's just no possible way to learn that apart from memorizing, right? We assume in almost all of machine learning there's some structure, right? For instance, we assume that things are linearly separable, or that there's a kernel function which makes them linearly separable, or blah, 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 right? That there is some structure and then I can learn a function within that structure, right? So, for instance, as an example here that I'll use as the running example in today's lecture, I'll assume that, that this, for instance, might be a Boolean function, a simple Boolean function. In particular, I'll assume maybe it's just a monotone conjunction, right? So what would that be? That this would be some, I'll describe this in a minute, this would be, say, some monotone conjunction. Something like, you know, if x3 is true and x5 is true and x7 is true, then you have the flu. In other words, it might be something like, you know, maybe I extract a whole bunch of features. I'm wearing blue jeans, I have black hair, I have a high temperature, you know, I have size 13 shoes, I have, you know, I have chills, blah, blah, blah. A bunch of those features are clearly irrelevant, and then there's going to be some subset of those features, which is going to be, you know, if I have a high temperature and I have the chills and I'm, you know, over the age of 35, that's indicative of the flu. Okay, so that would be a monotone conjunction. And my assumption is that this particular monotone conjunction comes from a class of all possible monotone conjunctions, right? And I don't know which is, my assumption is going to be, for the purposes of this illustrative example, is that there exists some good monotone conjunction, which is what I'm trying to learn. I just don't know which is the right one. And so I have to somehow learn the right monotone conjunction with a class of all possible monotone conjunctions. Now, this is really not that different than what you've been doing all along, right? So for instance, when you're doing linear regression, right? If you're doing linear regression with n features, then you know what the form, the class of the, that you're trying to learn. It's, you have a huge number of possible linear regressors that corresponds to all possible weighted linear functions, right? You're just trying to find the right one, right? There's going to be some linear function, some weights that you associate with features that comes from a class of all possible weighted linear functions. You want to find the right one. So it's the same sort of idea, right? So, and again, any linear, weighted linear classifier that you would have would classify a certain subset of all possible instances as being positive, and would classify the other ones as being negative, right? And you just want to find the right ones. So here I'm doing the same exact thing, except I'm doing it in the context of monotone conjunctions as my running example for the list of things. Okay, does that make sense? So really nothing different. I'm just codifying it in terms of stuff that you've done before. Okay. That's that. Okay. The next thing is, I'm going to assume that with respect to this instance space, that there is some underlying and unknown distribution over that instance space. There could be some D. I will endeavor to write bigger. This is one of my challenges, especially for those of you who are medic. Okay. What do I mean by this? I'm not going to assume that every possible bit vector is equally likely, right? In fact, it's almost certainly that it's not equally likely, right? So a bit vector corresponds to the features that I would have extracted from a patient. What dictates this D? What dictates this D is the patients that come through the door, right? So if I were to watch patients going through the emergency room at MGH every single day over time, I would say that, well, I see more of these sorts of bit vectors and less of those sorts of bit vectors, right? But I don't know what that distribution is until I guess I can learn that distribution by observing it over a long point in time. But my assumption is that there is some underlying but unknown distribution over this entire instance space. It's not necessarily uniform, and that's represented by this T. Okay? So that's just something that I have to deal with. It's the kind of data that I'm representing. Okay? Virgil may have talked about, one of the fundamental assumptions about machine learning is that typically you assume the future looks like the past, right? And that means that you assume that this D is effectively fixed over time, right? If it's the case that then the kind of data that you're being presented in the future looks nothing like the data in the past, then the machine learning can very much fail. And so again, here I'm assuming that this D is fixed, and in fact it is the thing which essentially is presenting me with the examples that I'm going to be seeing. Okay, all right, so I have that. Next, I'm going to say that, well, once I have this D, which tells me how likely it is that I'm going to see any particular instance within this instance space, and I have this underlying concept that I'm trying to learn, right, which is, again, the people that have the flu or really have monotone conjunction. I can also say, well, I can quantify, well, how good is anything else? Let's call this some other hypothesis H. Okay. Now again, in my concept, in my way of viewing it, if I can view H as being a subset of the instances, or you can think of it as a predictor, right? So if you think of it as a subset of the instances, it's basically the subset that it would predict to be true as a predictor, right? So, but here I'll draw it in this Venn diagram-y like way, where I'll think of it as a subset. It's the things which are assigned 1. And now I can talk about, well, where do H and C differ, right? And that's in some sense defines where H's errors are. And that would be this shaded region over here. It's essentially a symmetric difference between C and H, right? So in machine learning terms, right, this over here would be false negatives. These would be things that H would classify as not flu when they really are flu. And these over here would be false positives, right? These would be things which H classifies as being flu when they're really not. And it's really the sum of those two things which corresponds to my error region. These are errors, right? And if I want to talk about, so this is, again, error. And I can talk about the error of H, which I will define as the probability with respect to D that H and C differ. words, in terms of a process, you would think of it as, I'm going to draw an instance from X according to D. What is the likelihood that H and C are going to differ on their predictions? That's basically, what's the likelihood that the next patient coming in the door at MGH is going to be classified incorrectly with respect to flu? Okay, does that make sense? And again, it's not a matter of counting up how many things are in there. It's essentially how much is the weight of that stuff, right? And now, what I really want, of course, is to learn low error predictors. I want to find an H which is close to C with respect to this thing. I want the error to be, say, no more than 5%. Okay? We got this so far in terms of this mathematical abstraction? Okay. So, next, how does the machine learning tool actually get access to data, right? Now, you never talk about that. You get your data from Virgil, you get it from UC Irvine. Where is that data actually coming from? Right? So in this PAC model of learning, my assumption is that there is an example oracle. And this is an oracle. It's like a little box, and you can push a button. And what this thing does is it generates an instance according to D, and it classifies it according to C, and it hands it to you. Right? It basically says, hey, here's a patient, and here was what the right answer was. Right? Like if you were a resident working at MGH, your example oracle might be the chief resident, and patient walks in the door, and this chief resident says, this guy has the flu, you better learn it, right? So he's basically saying, you got a patient, walked in the door, the resident came and told you this guy's got the flu or doesn't have the flu, that's your example for the day. You could keep pushing that button, you keep getting more examples, right? Again, this is just a mathematical abstraction for what it means to get data, right? In your case, you typically just are handed a batch of data, but the assumption is that, in fact, that data was drawn randomly according to whatever natural process generates it, and then somebody gave you what the right answer is. Right? So again, every time you push this thing, you will get a labeled example. And that's what you get when you push this button. Now you can get as much of this as you want. Okay. Now, of course, a lot of what we're going to talk about is how much data do you really need from this example oracle to be able to learn and learn well? Okay, that's going to be the question. All right, we got all that so far? All right. Now we finally have all the pieces where I can actually state what the heck the PAC learning model is that involves all this stuff. And so let me do it on this board over here. Here's my big definition. And this is going to be lengthy. My apologies. I didn't make this up. So PAC learning is the following. I'll say let big C be a concept class over X. Okay. In our example, X might be bit vectors and C might be monotone conjunctions. Okay. We say that C is PAC learnable if there exists a learning algorithm called L with the following property. For all concepts C in C, okay, so for all concepts C in C, for all distributions D, okay, for any epsilon, where 0 is less than epsilon is less than 1. And then for any delta, just reminding any of these epsilon delta proofs from calculus, right? Sorry. If L is given access to an example oracle, and inputs epsilon and delta, then with probability at least 1 minus delta, L outputs concept H C, where error of H is less than or equal to 1. Okay? Take a breath. Let you finish writing that down. Let's talk about what this actually means. Here's what it means for something to be learnable. Okay? Learnability is with respect to certain concept classes. I'm not just going to talk about the world being learnable. I'm going to talk about, are monotone conjunctions learnable? Are linear functions learnable? Are blankety blankety blank learnable? Some things might be learnable, some things might not. Okay? So what I'm going to talk about is learnable or not learnable is a concept class. So this is saying, let's see it be a concept class, like the set of all possible monotone conjunctions. Okay? Over some instance space, in this case for monotone conjunctions, it would have to be over bit vectors. It's the way the monotone conjunctions could apply to. Okay? We say that monotone conjunctions are PAC learnable if there exists an algorithm which has the following property: no matter what monotone conjunction I give you, it could be, you know, x3 and x5 and x7, or it could be x1 and x2 and x3, or it could be whatever. Any monotone conjunction. For any monotone conjunction. For any distribution D over these instances, right? You know, it could be at this hospital, a different country. It doesn't matter what the distribution is. For any distribution whatsoever. For any error rate parameter between 0 and epsilon. For any confidence delta between 0 and 1. If the learning algorithm is given access to a source of examples, and it's told how accurate it has to be and with what confidence, it can, with high probability, produce a concept which has low error rate. In other words, if I tell you, you have to be 95% confident in producing a hypothesis which has no more than 1% error for any monotone conjunction, and you have a learning algorithm which can do it, then monotone conjunctions are learnable. Make sense? And so this is why it's called PAC learning, because you are probably, approximately correct. So I want to, with high probability, return something which is approximately correct. Okay, that's my goal. This is my definition for what it means for something to be learnable. Okay. And now, much of what you guys do falls within this model, right? You're given a bunch of different data, and then you are trying to, see if you can get 5% error rates, using a linear model or whatever, right? And you don't know what the right linear model is. It comes from the class of linear models. You have to find the right one such that, you end up with a low error. Okay? I want to see, well, what things are learnable and what things are not with respect to this definition. Okay? Does this make sense? Questions about this? Yes?
What's the difference? How do you quantify confidence and the error rate?
How do we quantify it? This is excellent, right? So these are free parameters, right? And now the question is, well, how much data do you need as a function of either delta or epsilon, right? So my guess is, and you're probably thinking about this already, right? What's going to happen if I tell you I want higher and higher accuracy? I say, no, 10% is okay today, but tomorrow I want 1%, the next day I want 0.01%. What do you think is going to have to happen? You're going to need more data, right? What if I tell you, no, you don't just have to be 95% likely to return something which is good. You have to be 99% likely. You have to be 99.9% likely, right? Then your sense is you're probably going to need more data still, right? But these are different things, right? I want to say, what is your confidence that you're going to produce something which is accurate, right? You could have low confidence that it's accurate, or you could have high confidence that it's not so accurate. Here I want you to have very high confidence that it's very accurate. Or again, arbitrarily high confidence that it is arbitrarily accurate. Okay, but these two things do trade off against each other. Okay? And they're different. Right? And again, because, why do I even need a confidence parameter? This is a good question. You need a confidence parameter because all of this is probabilistic. Right? You're getting data drawn at random from this thing. Like today, you might have just gotten a really bad draw of data. Like, what if I'm trying to learn from MGH's data today, but like today, whatever, like a busload of people got into an accident, showed up in the emergency room, nobody had the flu. It was just unusual because there was a big bus accident, right? Right? So the point is that this is a completely random process, and anything that's random, you can't be certain about what the outcome is going to be, right? You have to have some notion of, you have to give me some leeway to make a mistake because I've got a bad draw of data. That's what delta quantifies, right? And if you say that, no, I really want you to be confident that you've got something which is good, then I'm going to have to draw more data to make sure that my data isn't unusually bad, right? And then furthermore, if you want to have something which has a high accuracy, a low error rate, then you also know that you need to have a lot more data. But the question is, how much? Well, that's what we're going to try to answer, right? And what I want to show you is in fact precisely what the data requirements are as a function of epsilon, as a function of delta, and as a function of this, which we haven't talked about yet either, right? You probably also have a sense that if I'm learning some simple things, I probably don't require a lot of data, right? A monotone conjunction is a pretty simple Boolean formula, right? But you could have much more complicated Boolean formula. It'd be something like, x1 and x5 and not x7, or x3 and x2 and x5, and blah, 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 blah. You could have an arbitrarily complex Boolean function. And, for classes of much more complex Boolean functions, CNFs, DNFs, KCNFs, so on and so forth, your sense is probably I'll need more data. How much? Right? What is even the right, obviously these parameters are already well defined, right? I just give you an epsilon and delta. What is the right function of C? What is the right measure of the complexity of C that dictates how much data that you need? And I'm going to give you that.
How does this play into like how good a feature is? Like going with this example of the blue,
Yep.
take like a blood culture and you see what grows in it. Oh, okay, this is blue.
Yep.
You don't need that much data or that many features or anything. That alone would be able to tell you this person has.
And then you have exactly the opposite, right? So patients walk in the door, and what I extract from them is, what is your hair color, what is your eye color, what color tie do you have? Then you're not going to be able to predict the flu from that at all, right? Where that comes into play is that my fundamental assumption within PAC Learning is that there is a concept which will correctly classify your data. So for instance, in my particular case, if the features that I extracted at Mass General were hair color, shirt color, and blue jeans or not, then there would not exist any monotone conjunction of those features which would actually correctly classify my data, right? So in some sense, then the whole PAC Learning thing falls apart, right? So and then conversely, if I have God's magical features, like there's just one feature which perfectly predicts it, what that then means is that there would be a particularly simple concept class, which would be the one that you would be trying to learn. It would be like, give me the single feature which is perfectly correlated with the data, right? And then there's everything in between. So PAC Learning in some sense makes this fundamental assumption, in some sense, that you must have reasonable features and you must have some reasonable concept class that you're trying to learn. Again, this is a theoretical model, right? The reality is messier, right? The reality is more like what you're saying. Like I don't know necessarily what the right features are, whether my features are good or not, even whether the concept class that I'm trying to learn, linear functions, more vector machines, whatever, is the right function, right? But this is saying that, well, even if you did have all that right, you knew that here was the concept class, you knew you were trying to learn a monotone conjunction, you're trying to learn linear function, I can tell you how much data you're going to need if such a linear function, if there's a good one out there that you can find. Right? You can think of it the following way. It's like your machine learning process is going to be something like, I'm going to try logistic regression, right? And now, what PAC Learning is going to be able to tell you is that assuming that a good logistic regressor exists, right, with respect to the features that you've extracted, okay, how much data would you need, right? And of course, that assumption could be false, It may be that there is no good logistic regressor for the features that you extracted, in which case then what PAC Learning tells you is wrong. Well, it's not wrong, it's just it's working under assumption. If it falls apart, then it's telling you that one of your assumptions was wrong. That is, either logistic regression is not a good classifier and or your features are bad. Right? But this is basically saying under those assumptions, right, that you have a set of features and a classifier class that works, and you just have to find the right one. Here's how much data you would need. Make sense? I hope that answers your question. Max?
Sure. So in the context of like you have perfect features that correlate, have correlation one target, what is the difference between a concept class, which like, let's say X1 is a perfect feature?
Yep.
What's the difference between the concept class X1 and X1 or X2 or X3?
Right. Right, so here, my concept class is going to be a set of possible classifiers. And so, for instance, within the set of all monotone conjunctions, X1 is one of them, right? What is a monotone conjunction? It is a subset of features that you AND together, right? Well, you have a trivial subset of features, you just have one of them, right? So it's within the class of things that I'm trying to learn. I'm trying to find the right one. So, all right, any other questions? I'm trying to move on to actually start doing some fun stuff. See if we can build some things like this, improve some things about this. Okay? All right, let me leave this up here for now. Let me work on this board, and eventually we'll have to erase that. Okay? So let's actually then see, well, you know, are things PAC learnable? Yes or no? For instance, can I learn this? You know, how would I do it? How would I build a classifier which does this? Again, I'm going to assume that there is an underlying and unknown monotone conjunction. I don't know what it is. I have to find it. Okay? And now I want to point out that you don't want to do this by brute force. Why? Let's get back to Max's question here, right? Well, so X1 is a perfectly good monotone conjunction. So is X2 and X3. So is X1 and X2, X2 and X3, so on and so forth. How many possible monotone conjunctions are there over bit vectors of size n? Louder? Yeah, it's 2 to the n, right? In fact, I actually gave it away earlier because I said that a monotone conjunction is the logical AND of a subset of your features. Well, how many subsets of size n do you have? Well, there's 2 to the n possible subsets. So there's 2 to the n possible monotone conjunctions. You can't brute force it, right? You can't just go check them all and find which one is good because that's going to be exponential time. Okay? So we have to be more intelligent, right? And so how would we be more intelligent? So let's see. By the way, I keep using this word monotone. What does monotone mean? I don't have negated variables. All of my variables are just positive. I don't have things like not x1 and x2 and x3. Just everything is negated. Okay? So then that's what monotone conjunctions are. What was the example that I had? I should have kept it. It was x3, 5, and 7?
Yeah.
So here's an algorithm for learning monotone conjunctions, okay, under this PAC Learning model. Okay, I'm going to show you that it is possible for me to draw a fixed amount of data, a fixed amount of data from my example oracle, which is going to be a function of certainly epsilon and delta. And it's going to end up being a function of n as well, which is my bit vector space. I'm going to show you how much data I need as a function of n, epsilon, and delta. And I'm going to give you an algorithm which is provably guaranteed to, with high probability, produce a hypothesis which has an error rate which is no more than epsilon. Okay, so we're going to build a PAC Learning algorithm for this problem. It's going to be a one-off. It's not going to be a general thing. It's going to be for this specific problem. Okay, and let's see how we can do it. Okay, so I'm going to take advantage of the following property. Okay, here's how my algorithm is going to work. Okay. I am going to start off with this is my hypothesis. I'm going to say that's my initial guess as to what my hypothesis is. Okay? Now, I claim that this particular hypothesis has a nice property. Think about all positive examples and negative examples. Okay? I claim that this hypothesis will never make a mistake on one of those two things. Which one will it never make a mistake on? I claim that this thing will either never make a mistake on positive examples or it will never make a mistake on negative examples. One or the other. Again, what does it mean for an example to be positive or negative, right? So let's take some bit vectors. This is an example. Suppose that my true hypothesis is this, x3 and x5 and x7. So I chose, unfortunately, 7 things. So suppose I'm just going to draw some random bit vectors, 0, 0, 1, 0, 4, 0. I just grab some random bit vectors. Are these things positive or negative examples? So this x3, x5, x7, those are all 1s. This is going to be labeled with 1. Right? Here, x3, x5, x7, this is also labeled with 1. Here, x3 is a 0. So this is going to be labeled as a 0. So on and so forth. So you see what this means, right? So this is how this concept would classify this data. Now, of course, what you're given is you're given data that looks like this, and you have to reconstruct that. Now, my question is, that's starting hypothesis. You're going to be given a bunch of positive and negative examples. I claim that it's never going to make a mistake on either the positive examples or the negative examples. Which one? Negative. It will never make mistakes on negative examples. Why? Because for an example to be negative, if this is my classifier, for an example to be negative, one of these 3 things at least has to be 0. That's what makes the example negative. In fact, for this thing over here, this was negative precisely because x3 was 0. Right? These things were not negative because none of the things were 0. Okay? So every negative example has at least 1 0 for one of those variables. And notice that that thing has every one of the variables. So it will also be negative. So this never makes a mistake on negative examples. Okay, I'm on practice. My handwriting's atrocious. Now, so I don't even have to look at the negative examples. I know I'm going to get them all right. Okay? If I want to improve that, how do I improve it? I would look at the positive examples, and what can I learn? Okay? If this is a positive example, what does it tell me about that hypothesis? Can x1 be in the hypothesis? Can x1 be in the final classifier if this is a positive example? Yes or no? No, right? The variable x1, if somebody shows this to me as my positive example, and I see that there's a 0 here, that means that this variable cannot be in the final hypothesis, because otherwise, if it were in the final hypothesis, this thing would be labeled 0 properly. So every single place where there's a 0, I can knock out those variables. I can immediately say, x1 can't be in there, x2 can't be in there, x4 can't be in there, blah, blah, blah. And then I just keep going down with the next one, so on and so forth. And notice that I'm only knocking out variables which I know for a fact can't be in the hypothesis. I'm never going to get to the point where I knock out variables by accident which are going to cause me to make a mistake here. Never, right? So I never have to look at these negative examples. All I have to do is look at the positive examples. And I can winnow my thing down further and further. And I'm going to be getting closer and closer to having the right subset of variables. Okay? In principle, if I looked at the entire data set, right, I would get down to the point where I'd just be left with these 3 things. Okay? But what's going to happen is as I get more and more data, I'll get closer and closer to this. Okay? And now the question is, well, how much data do I need until I get down to something which is close to being right? Right? Because, again, what's my goal? Well, in an ideal world, I get this, which of course has 0 error rate. But my boss didn't tell me you had to have 0 error rate. In fact, if your boss ever told you you had to have 0 error rate, you're in the wrong line of work. Right? Not our line of work. It's never going to happen. All I have to do is I just have to make sure that I get down to some function which is within epsilon of being correct. So how much data do I need until I get there? Okay? So now we have to be a little more clever. We have to define sort of, good and bad variables. Right? So obviously, x3 and x5 and x7 are all the right variable. I never want to worry about those. But then for all the other ones, x1, x2, x4, x6, x8, so on and so forth, I claim that some of those are worse than others. Okay? What do I mean by that? Well, what would cause one of those variables to be bad? What would cause x1 to be a bad variable? x1 would be a bad variable if there are lots of positive examples that have x1 0. Right? That's what would cause x1 to be a bad variable. Okay? Now, what if this were the only instance ever in my entire data set where x1 was 0? Well, then x1's not such a bad thing to have inside your hypothesis, because then you're only going to make a mistake in one place. Right? So if there weren't many places where you had positive examples where x1 was 0, then who cares? You could have x1 in there, it doesn't hurt you too much. Having x1 is a bad thing if there are lots of positive examples where x1 is 0. Okay? So I'm going to define a bad variable to be one where the probability that I have instances, that I have positive instances where that variable is 0 is high. That makes it bad. Okay? Does that make sense? So a variable is bad if it's not in the concept, sorry, big C, little c. So if the literal is not in the concept I'm trying to learn, obviously none of these things can be bad by definition. They're in the concept. So if the variable is not in the concept I'm trying to learn, and the probability of drawing instances D where where xi is 0 and c of x is equal to 0. Okay? That's a bad one. Okay? That's going to cause me to make a lot of mistakes. Okay? In fact, I want to quantify that. I'm going to say it's bad if it's only happens once, I don't care. Okay? I'm going to say that it's bad if that happens at least epsilon over n times. Now that was chosen carefully, right? Because we certainly have this intuitive sense that, sure, you could have a literal which is not the right literal, but if it happens like 1 out of a billion times, who cares? But if this happens enough, it's going to cause problems. And I'm claiming that's what it means to be enough, right? Why? Well, certainly this epsilon should come into play somehow. It's just a fact, and I'm claiming your underlying n is going to come into play as well. How many total bad literals can you possibly have? N, right? There's no more than n literals in total, variables in total, okay? And what I'm going to claim is that a literal is going to be bad if the sum over all the bad things would then blow my error budget. I want to get rid of, if I can get rid of everything that's bad, that is, if I get rid of all of these bad things, then the only things that are left, bad ones that are left, right, are ones where this is less than epsilon over n. And now there's no more than n of them. Therefore, if I sum up all of their bad contributions, it's no more than epsilon. Does that make sense? So I want to get rid of all these things. Because on the ones that are left, I don't care if they're in there. They're going to contribute to no more than epsilon error. Got me? Good. All right, now my goal is, how can I be guaranteed to get rid of all these bad ones? Okay, that's what I want to do. All right. Is this? I'm going to get rid of this by keep pushing this button, right? And then removing all the variables where I see that it's positive and the variable is 0. That process that I was just showing you. I'm going to keep doing that. How much do I have to do that until I guarantee with high probability I've gotten rid of all the bad variables? Well, that's what I want to try to quantify. Okay, I'm going to do this right now. Okay? So here's what I want you to think about. Suppose that I fixate on one particular bad literal. We had x1 was that's why I keep saying literal, variable, same thing. Suppose I have fixated on one particular bad variable. What's the probability that that bad variable is going to be killed by a single randomly chosen example. Okay? So the probability that a bad variable survives one randomly chosen example. Okay? That is, I push that thing once, okay? I check to see, does it knock out x1? What's the chance if I push that thing that it knocks out x1? Okay? Again, well, the definition of a bad literal is that if you choose examples according to D at random, there is at least an epsilon over n chance that they're going to have this property that it's 0 when the thing is 1. Okay? So the chance that it survives this is what? Well, there's a chance, there's basically an epsilon over n chance that you're going to find something which kills it. But that means that there is a what chance that it survives? 1 minus epsilon over n. Okay? So this is at least 1 minus epsilon over n. That's the chance that it survives. Actually, at most 1 minus epsilon over n. Okay? So there's at most a 1 minus epsilon over n chance that it survives a single draw from EX, right? Because there is an epsilon over n chance that you get a positive example where this thing is 0 and then you kill it. Okay? So this is the survival chance. Now, well, that's high, but what do? I keep pushing the button. What's the chance, the probability that a bad literal survives m randomly chosen examples? Well, it has to survive the first random, and it has to survive the second one, and the third one, and the fourth one. So what's the chance that it survives all m of them? Raised to the m, right? Okay. Now, so then what's the probability that there exists some bad literal that survives all m? Okay? Well, this is the chance that any one of them survives, okay? But now there's a whole bunch of them that might survive, right? So if there's a 1% chance that any one of them survives, and then there's like 10 of them, then the chance that one of those 10 might survive is now, each one of them adds up, right? There might be a 1% chance this one survives, or a 1% chance that one survives, or a 1% chance that one survives. If there's 10 of them, I gotta multiply by 10. How many bad literals are there at most? N. No more than n times this, right? Because there's no more than n of them. Each one could contribute as much as this much, and there's no more than that. Okay? Now, this is the chance that something bad survives. If nothing bad survives, by the way that I've set this up, my error rate's going to be good. If I got rid of all the bad things, the only thing that was left are good things, and good things contribute no more than epsilon over n, and there's no more than n of them, my error rate's less than epsilon, right, as we discussed. If I can get rid of all the bad things, I win. Okay? What's the chance that I have to win? My boss has told me you have to be correct with what probability? At least 1 minus delta. In other words, your failure rate has to be no more than delta. I need this to be, this is what you need. I need to have my failure rate is no more than delta. So I have to pick m large enough such that n times 1 minus epsilon over n to the m is less than or equal to delta. Right? Now I just have to solve for m. And then I'm good. That tells me how much data I need. It's good, right? Okay. So let's do some math. All right. So that's going to be equivalent to what? I'm going to have 1 minus epsilon over n to the m. That's less than or equal to delta over n. That's going to be the same as doing m times the natural log 1 minus epsilon over n. Log and delta over n. I'm going to solve for m, right? Is this positive or negative? It's quantity. What's natural log of 1? 0. Natural log of something less than 1? Negative. If I divide by this thing, then I got a swap that sign, right? Sorry for you guys in the back, and I'll write this bigger in a minute, I promise. Okay, so I need m bigger than or equal to natural log delta over n divided by natural log, okay. This is a little funny in that writing it in this way because, first of all, this is negative, and this one's also negative, right? Because delta is something which is less than 1 you're dividing by n. So typically, you write it this way, natural log of n over delta divided by natural log of negative natural log 1 minus epsilon over n. And then even that, we want to simplify to make it a little cleaner. We have to deal with this thing. So I was going to derive this for you, but in the interest of time, I won't. So I claim that the following thing is true. So 1 over negative of the natural log of 1 minus x. Write it down here because we're going to need it in 2 different ways in a minute. This is less than or equal to 1 over x and bigger than or equal to 1 minus x over x. Okay. This is not too hard to prove. You can prove this using the Taylor series expansion for natural log of 1 plus x. I won't go through the details unless you want to do that kind of fun math. But this shows up all over the place when you're doing PAC Learning, so it's just a good fact to know. But it's basically just the consequence of you do the Taylor series expansion of natural log of 1 minus x, and you basically either drop some terms or do some simplification, and you can get that this is true. Okay? What this means is that this 1 over negative natural log 1 minus epsilon over n is basically just 1 over that x. It's just n over epsilon. So when I would say this, I would say since 1 over x is bigger than or equal to 1 over negative natural log of 1 minus x, this implies that n equal to, again, x in this context is epsilon over n. Then if you use n over epsilon natural log and delta, that would be bigger than or equal to this thing. And this suffices. It's a much cleaner form. Okay? So we've got an answer. This is my answer. Fine. Okay? My answer is I can actually learn monotone conjunctions. And all I have to do is I draw n over epsilon natural log n over delta examples. That's how big my data set has to be. I run the algorithm that I showed you to basically kill all I start with all the literals and I keep knocking them out every time I see a possible example where there's a 0. What I'm left with is guaranteed with high probability greater than 1 minus delta to have an error rate no more than epsilon. As long as this is how much data I start with. Make sense? Okay. Now you'll start to immediately notice some things if you sort of look at this formula. Okay. Notice that, as is true in life, it's much easier to be confident than accurate, as people often are. In other words, that if somebody tells me to increase your confidence by a factor of 10, I only have to increase my data requirements by a natural log of something, right? Whereas if I need to increase my accuracy or decrease my error rate by a factor of 10, then my data requirements go by a factor of 10. Right? Do you see that? Right? So the data requirements are a function of 1 over epsilon, whereas the confidence requirements, the data requirements for confidence, is a function of log 1 over delta. So there's an exponential difference between accuracy and confidence. This gets back to some question, I forget who was it here, But somebody was saying, well, what's the difference between accuracy and confidence? What consequences do those have? And this is sort of an interesting thing that PAC Learning is telling us about machine learning, is that it's easy to have high confidence. It's a little bit harder to have high accuracy. Much data. Okay? We see this? And then you also, at least for this example, maybe that's not true always. Who knows, right? And then notice that there's a few caveats here. I've only given you an algorithm for learning monotone conjunctions. I haven't done all of machine learning, obviously. Furthermore, I've told you this is the data requirements for the particular algorithm that I gave you. Right? Maybe there's a much better algorithm, which is much smarter, which needs less data. Who knows? But for this particular algorithm, for learning this particular concept class, these are the data requirements. Okay? Now, I'm analyzing this one in particular because it turns out that all of machine learning looks just like this. It's 1 over epsilon log 1 over delta and some stuff. Okay? And effectively, if you remember, I was telling you that, well, somehow the complexity of this is going to have to come into play, which we haven't really quantified yet. It's coming into play here sneakily with this n log n, as it turns out. But I'm going to show you, not so sneakily, how it really comes into play. Okay? Everybody get this? With me so far? Good. Let's do some more. Okay? This is all well and good, except you know, this would make machine learning and PAC learning a pain, right? Every time you give me something new thing, like I have to do a linear classifier, I have to do, you know, KCNF, I have to do whatever, I'm going to have to invent some new crazy algorithm and some new crazy analysis to be able to figure out just how much data I need. And I'm not going to be really sure whether it's the best algorithm or whatever, right? It's not clean in that sense. Okay? Let me give you sort of the uber algorithm for all of PAC learning, which you can actually prove really nice things about, this uber algorithm. Okay. Here's the uber algorithm. Let's see. Keep this somewhere hidden. Hidden in plain sight. Here. Okay. We erase our lovely definition. So let me talk about what this uber algorithm is. This particular algorithm had a certain characteristic I claim in the end, right? I started off with this hypothesis, which was the conjunction of all the literals. It was guaranteed to not make any mistakes on negative examples. And then every single time I looked at the positive examples, I removed the variables that it would have made a mistake on. So that in the end, what I'm left with is actually guaranteed to correctly classify everything that I've seen. It's going to get all the negative ones right for sure, and I fixed it to make sure I got all the positive ones right. So in the end, what I've really got is, I've got a monotone conjunction which correctly classifies all of the data that was given. Okay? I'm going to have that be my uber algorithm. My uber algorithm is going to be, I'm going to draw a sufficiently large amount of data, and then I'm just going to return any hypothesis which is consistent with the data. And I'm going to show you that that algorithm, again, I don't have to tell you what that algorithm is. All I know is draw a large amount of data, return anything which is consistent with it. Done. I'm going to show you what the data requirements of that is. Whereas this is just one instance of that algorithm. Okay? Now I'm going to show you that this is a general machine learning thing. I don't care what your hypothesis class is. I don't care if it's linear functions, quadratic functions, you know, blah, blah, blah. Draw a sufficiently large amount of data. Find any hypothesis which is consistent with it. You'll be set. That's it. And this is more or less mimicking what goes on right now in all the machine learning tools you did, right? What is logistic regression doing, or linear regression? It's just constantly trying to fix the weights to make sure that I get everything right. You want to drive your training error down to 0, right? With the hope that then you have a sufficient amount of data that your testing generalization error will be low, right? Well, I'm going to codify that perfectly. I'm going to say, if you have a sufficient amount of data, and you return something which perfectly classifies all of your data, you will do well. Finished. Full stop. Okay? That's the uber algorithm. Everything. Okay? All right. How can we analyze that? I'm going to analyze it sort of like the way I did this one, okay? Except now I'm going to say, again, so in my Uber algorithm, I'm making this up by the way. This is Uber in the German sense, not in the car sense. Okay. And this is not in the literature anyway. I just made this term up. This is the overall arching algorithm, right? Is again, draw a large amount of data. Okay, I'm going to define what large is quite carefully in a minute. And then return any C in C, which is consistent with the data. Done. Okay? I want to define what n is. How large does that amount of data have to be? Such that if I just do that, that's my whole PAC Learning algorithm. If I just do that, then I'm guaranteed to satisfy the PAC Learning conditions. With high probability, I will return something which is accurate. Okay? And this basically, this takes away all of the, in some sense, remember all the work that we had to do here for this problem? We had to decide, oh, I'm going to have to define bad literals, I'm going to have to assign what is good and bad in terms of epsilon over n, carefully chosen, blah, blah, blah. You don't have to think about any of that anymore. All you have to do is draw a bunch of data and then find something which is consistent with it. You basically turn machine learning into a purely algorithmic task, right? I just say, here's a bunch of data, give me something consistent. No sampling, no analysis, no nothing. Just an algorithm. Okay? We're going to do one unified analysis. Okay? How big does that have to be? So what I'm going to do now is I'm going to say, well, over here I had to define these good and bad literals. Over there I'm going to define good and bad concepts. Right? So I'm going to say that a concept, a hypothesis, H in C is good if the error of H is less than or equal to epsilon. I'm happy with any of those things. And then a hypothesis is bad if the error rate is high. That's what it means to be bad. Okay? Now, I want to take the spirit of that last proof. What's the spirit of this thing? It's going to be, what's the chance that if I focus on one particular bad hypothesis, what's the chance that it gets killed by a single randomly chosen example? Okay? What's the chance that a bad hypothesis survives m randomly chosen examples? What's the chance that there exists any bad hypothesis whatsoever that survives m randomly chosen examples? I want to choose m big enough to guarantee that that chance is small. That mirrors exactly this analysis over here. Okay? So let's do that. So what's the probability that now a bad hypothesis survives a randomly chosen example? Okay. Well, how does it survive it? Well, again, remember, a hypothesis is bad if its error rate is high. If its error rate is high, that means that if you were to choose an example at random, there's at least an epsilon chance that it's going to be wrong. But if the hypothesis is wrong, it gets killed. That's the whole point, right? I'm only going to return hypotheses which are consistent with my data. So that hypothesis would not be consistent with the data point because it's wrong on it, right? So what's the chance that a bad hypothesis survives one example? Well, the chance that it would be killed is at least epsilon. The chance it survives is at most 1 minus epsilon. Okay? Looks like it is up there, right? What's the chance that it survives m examples? Okay? Well, that's going to be less than 1 minus epsilon to the m. It has to survive the first example, and the second one, and the third one, and the fourth one. And each one of those things is going to survive with probably 1 minus epsilon. What's the chance that some bad hypothesis survives this? Well, there might be one bad hypothesis which has that chance of survival, and then there's another one, and a third one, and a fourth one, and they all add up potentially. How many bad hypotheses can there possibly be? Sorry? Well, 2 raised to the n if I'm talking about Boolean functions, right? But if I'm talking about logistic regression, it's something different, right? Remember the whole point of PAC Learning, which I erased again, there it is up here. It's the number of concepts in my concept class. It's 2 to the n for Boolean functions, but it might be something different in another place, right? So I claim this is no more than the size of C. Right? This is the total number of concepts that exist. There's certainly no more than that bad number, right? Okay? So certainly no more than C. And again, and for Boolean functions, this is no more than 2 to the n. For more complicated functions, I'm sorry, for not Boolean functions, for monotone conjunctions, it's 2 to the n. For more complicated Boolean functions, this might be much bigger, right? It might be 4 to the n, or whatever, right? But it's, there's some number. This, I want this to now be less than or equal to that, right? And now I just have to do the same exact process, okay? And if you run through the math, you're going to see what's going to be true. Over here, I had this, right? I had n times 1 minus log raised to the n less than or equal to delta. Ended up being this over here. You got this epsilon over n became that thing over there. And then this n over here, which is now going to be c, shows up on the top over there. So if you run through the math, you're going to get that m has to be bigger than or equal to, I'm sorry, m equal to 1 over epsilon natural log c over delta slices. Just the same exact correcting that I did over there. Right. It's epsilon over n, which is now for us just an epsilon. Here it became an n over epsilon. For us, it's just going to be 1 over epsilon. And then this n over here, which for us is a c, became part of the delta. Right? Okay. So for this Uber algorithm, again, if I have a concept class I'm trying to learn, and I have an accuracy requirement and a confidence requirement, all I have to do is draw this many examples, 1 over epsilon natural log c over delta, and then I find any concept whatsoever, which is consistent with my data, and it's going to be guaranteed to meet the PAC Learning conditions.
So since this is the Uber algorithm,
Yep.
if we apply the same to the monotone conjunction, then we are missing n over here.
I know. In fact, this one's better. It turns out. In fact, exactly that, right? So, so note, right? What you're pointing out is this. For monotone conjunctions, I have that the size of C is equal to 2 to the n, right? In which case, this algorithm over here tells me that I really only needed, 1 over epsilon natural log 2 to the n over delta, which is just going to be, there's a natural log 2 here, but it's basically n over epsilon times natural log 2 plus 1 over epsilon natural log 1. It's better, right? You could think of it as if I were to, essentially the difference between these two things is you get like this n over epsilon. This one has this extra n over here, which you don't need. Right, so this is basically off by a log-in factor. It's excessive. Yes?
So if you had a continuous feature with C being infinitely large,
Yeah. Normally you'd pay people to be in the audience to be plants, so they would ask questions like this. Come see me afterward. Maybe I'll tell Virgil to add point. It's a great point. So here's the question, right? So from all the examples I've been using, the only example I've been using so far, monotone conjunctions, is a discrete function for which the size of the concept class is has some discrete value. Maybe large, maybe exponential, but the point is it's not continuous, right? What if you have linear regression? How many linear regressors are there? Infinite, right? Because your parameters to linear regression are real valued coefficients, right? So this lovely Uber algorithm seems fabulous right up until the point in time where this becomes continuous, and then it tells you nothing.
But for the purposes of a concept class, 2 hypotheses are
does that sound like?
Easy to mention.
Oh, that sounds like VC dimension. Okay. There's probably some reason why Virgil gave you this information. These are all excellent, excellent things. Now let's actually do that. Okay. So here's the point. This is fabulous. This is great. This makes a lot of sense only for discrete things. It makes no sense for continuous things. Because again, for continuous things, the size of my concept class is infinite. But is it really the case that these infinite concept classes have infinite complexity? And I'm claiming that they don't, right? Here, in some sense, if you think about it, here's what I want you to think about. I'm going to rewrite this in the following way, right? This is 1 over epsilon natural log c plus 1 over epsilon natural log 1. Okay? I want to break this up into 3 different parts. In some sense, there's a piece of this which basically says, here's my complexity with respect to epsilon. Here's my complexity with respect to delta. And this is effectively the complexity with respect to your consequence. Right? That's what this is saying. It's basically saying that the complexity measure that I'm using for your concept class is the log of its size. Okay? Effectively. That's how I told you I was going to set this thing up to begin with. I was going to say that we know that data requirements are a function of how accurate you have to be, how confident you have to be, how complex of a task you're trying to solve. There it is. So the complexity measure for accuracy is 1 over the accuracy requirement. The complexity measure for confidence is log of 1 over the delta. The complexity measure of the concept class you're trying to learn, at least in this model, is log of the size of the concept class, which falls apart when you're talking about infinite concept class. We need a different complexity measure. And it turns out that the right complexity measure is easy. Okay. So let's get there. How much time do I have, actually? Is it 4:30? I have until. So let's try to get to as much of this as I can. And spend days and days. I taught an entire course just on this, whole term. Do all that. Okay, so let's do more. It's a great question. So first of all, are infinite concept classes even learnable? Maybe this is correct. Maybe infinite concept classes really aren't PAC learnable. Like really the best you can do for is just to hope and pray like you guys do right now. Just mark up data and see what happens. You can never be guaranteed. So I want to argue to you or with you or show you that in fact, yes, I can PAC learn infinite concept classes. Okay? And then furthermore, I want to come up with the equivalent of the Uber algorithm but for infinite concept classes, which I will do. You guys enjoying this? You can say no. Virgil hates this stuff. It's the first thing he cuts out of the course when I don't teach it. So I'm glad I could be. I guess you should say he hates it. It's not his thing. All right. Let's take the simplest imaginable infinite concept class, essentially a linear classifier in 1 dimension. What does that mean, right? So I'm going to give you this. My instance space X is going to be 0, 1. Okay? Basically, you just have the unit interval. Okay? And my concepts are just going to be half planes, half intervals. My concept C is half intervals. Okay? So like for instance, you'd have a threshold T. You'd say that C with respect to T of X is equal to 1, if X is bigger than or equal to. Okay. So you're just trying to learn how. Simplest imaginable. Whoops, I did it backwards. Actually, my notes, can I switch this? Match my notes to make sure I don't do any of that. all the positive things are here. Happens. Okay. Now, what's the size of this concept class? Well, the concepts are defined by thresholds. There's an infinite number of thresholds. It's infinite. Okay. But is this thing really of infinite complexity? It sure doesn't seem so, right? Even though there's an infinite number of those things, it's probably not hard to find a good one. So I'm gonna show you that in fact there's a pretty simple algorithm which I can pretty easily prove actually meets all the PAC learning criteria, even though this is an infinite concept class. So that means that infinite things really are learnable, even in the PAC sense, and that means that we really have to do something different than what's that is over there. So here's my PAC learning algorithm. For this particular, I am going to I'm going to draw a large number of examples. I have to output a threshold, right? The threshold that I output is the largest positive example that I see. In other words, my PAC learning process would be like this. I'd be pushing that example oracle, push it, and I see a positive example, a negative example, a positive example, a negative example, positive, negative, and then eventually I quit and I say, this is the largest positive one I saw, that's what I have. That's my hypothesis, done. It's the largest one that I saw. Okay? Now, what's true about that hypothesis that I output? I claim, and this goes back to you're noticing some patterns here probably, I claim this can only make mistakes on one kind of thing. Does it ever make mistakes on positive examples? And does it ever make mistakes on negative examples? It can make mistakes on positive examples. Why? Okay. I claim that where is the right threshold? The right threshold is somewhere in here. I don't know where it is, right? I know that the right threshold is not to the left of this because there's a positive example over there. I also know that the right threshold is not to the right of that because there's a negative example here. But there's this gray zone in here, right? Where the right threshold might be, okay? And I claim that it can only make mistakes on positive examples, right? There can't be any negative examples. We know that this is all the positive range for sure, right? But there might be some positives over here which I mistakenly classified as negative. Okay? So it's only going to make a mistake on one kind of examples. Okay? I want to analyze this particular algorithm. How much data do I need until I guarantee that the fraction of positive examples I make mistakes on is small? I know I'm not going to make any mistakes on negative examples. Okay? So there's a pretty simple way to think about it, and that's the following thing. I am going to imagine this. Here's my true hypothesis is a threshold t. Right? That's the true answer. Okay? I'm going to define the following thing. I'm going to say there's a region here where the distribution associated with this region is equal to epsilon. Okay? So I'm going to say from this threshold, I'm going to walk backwards. And as I take up more and more of this space, I'm going to, remember D is a distribution over this entire range. There's a certain probability that you're going to see any one of these values. I want to define a region whose weight is epsilon. And I want that region to be the region whose rightmost boundary is tau, and whose leftmost boundary is such that then the weight of this thing is epsilon. I mean, that exists. That region exists. For the purposes of analysis, I'm going to say, let's consider that region. Okay? Now, here's how I'm going to use this to analyze my problem. Okay? I claim that as long as I see any example within this region, I'm set. Why? Okay. Because first of all these things are positive, right? This is the threshold. If I see any example inside here, going to be a positive example, and it's going to define my threshold, and I'm only going to make mistakes to the things to the right of it. And I'm never going to make mistakes over there, because those are negative examples. I'm only going to make mistakes from that are going to correspond to where the positive example is up until the threshold. And now, if I get a positive example inside this region, and this region has weight epsilon, right? That means that the stuff to the right of that positive example has weight no more than epsilon. The problem is going to be if I don't have any positive examples in this region, that is, I'm only over here, then I have a lot more stuff I'm making mistakes on. Does that make sense? So I claim that my analysis is actually quite simple. All I have to say is, how many examples do I have to draw such that I'm guaranteed to get at least one example in this epsilon region? That's it. As long as I get at least one example in epsilon region, I'm set. Okay? Make sense? So, this proof is going to feel a lot like all the other proofs that we did, right? What's the chance that I miss this region with a single example? It's going to be 1 minus epsilon. So I'm going to say probability that I miss region with one example, that's going to be at most 1 minus epsilon. What's the probability that I miss the region with m examples? It's less than 1 minus epsilon. M, right? I want this probability to be no more than delta. I want the chance that with all m examples, I miss this region entirely. As long as that chance is less than delta, then I'm set. That means that with probably at least 1 minus delta, I have at least one example inside that region, and I'm good. So then I just have to solve for this thing, and then you get that m equal to 1 over epsilon. Natural 1 over delta. Okay. You notice the same thing showing up all over again. 1 over epsilon, log 1 over delta, don't forget. Okay? Yes?
How does this framework deal with noise? So if it,
I have to pay you too. How many, there's going to be so many people getting A's in the class I'm talking about. Yes? Noise?
so if there's one odd example at 1 where it's positive.
Yep. See, I have to pay you double because in fact I wrote my entire PhD thesis on this. I kid you not. So we'll get there, maybe. So the answer is this handles noise very badly, very badly. Okay? So in fact, just as a history thing, 30 seconds, right? So this PAC Learning framework came out. It was a beautiful thing. People got really excited about it. You started seeing all these kinds of patterns. It made all the sense in the world. People started developing, hundreds and hundreds of papers being written about PAC learning conjunctions, PAC learning linear regression, PAC learning neural networks, PAC learning blah, blah, blah. They developed all these kinds of algorithms, Uber algorithm, everything else, and then they put them in practice and they all sucked. Okay. Why? Because in the real world, there's always noise. And there's either real noise, that is labels are just mistaken, or what is more true is that the thing you're trying to learn, like a linear regressor, doesn't perfectly fit your data. Right? Maybe a linear regressor gets down to like 1% error, but effectively from the perspective of the algorithm, the other 1% looks like noise. Right? And then this whole thing falls apart. Okay? So that was the state of the world when I started my PhD. And then people worked really hard to figure out how can we fix PAC learning so that then it can tolerate noise. And even more interestingly, and this is what I did my PhD on, is how much does noise impact data requirements? Okay. If this is the answer in the absence of noise, how much does it change when you start adding noise? Because we have a suspicion that the more noise you have, the more data you're going to need. How much does it depend upon the amount of noise? And we can perfectly quantify that too. So, I'm not going to have enough time for that today. Maybe I'll try to give you the punchline if I have it. Okay. That's a great question. Any others? Yes, noise is bad. Noise is present everywhere. All right, so my punchline here is that in fact, infinite things are learnable. In fact, this is even learnable easier than that, and easier than learning monotone conjunctions, right? Remember, monotone conjunctions was like this, and it had some ends in there too, right? So this even requires less data, despite the fact that it's infinite. And the answer here is that the size of the concept class is not the right complexity measure for a concept class. I'm sorry, the natural log of the size of the concept class. Remember, this sort of setup, you can think of it as essentially saying this is in some sense the complexity measure of the problem I'm trying to solve. It's the log of the size of the concept class. This sort of dictates that, or indicates that in fact that's not true. Things which are infinite size really are learnable, so that's not the right complexity measure. Okay? So it turns out that, and this is a proof I can't do today because it would take a whole lecture just by itself, that one of the most interesting early results in PAC Learning was to show that in fact there is a much better complexity measure for a concept class, and it involves VC dimension. And so let me give you what that theorem is, and I will unfortunately not be able to prove it for you, but it's a really beautiful proof. Takes too long. So here's the result, which is sort of the equivalent of this Uber algorithm.
So we talked about
You want an A2. You're going to try to make a good question.
We talked about the lower bound, right? So you mentioned there is upper bound as well. So
Yes.
what's that?
I will show you both. In fact, that's really cool. In fact, I'm going to give you a theorem. That is a really good question. This is not just 2 steps ahead of what I'm doing. So save the question. I'll do it. So I'm going to give you the equivalent of the Uber algorithm, but now for infinite concept classes. Okay? It's the same exact algorithm in some sense. The algorithm is draw a large amount of data and return any concept in your class which is consistent with the data. But now the amount of data is not this, because this doesn't work for infinite concept classes. The amount of data is this. M is equal to something which is on the order of d over epsilon, natural log 1 over epsilon plus 1 over epsilon, natural log where d is the VC dimension of C. That's the right thing. Okay, now, I'm actually cheating. That's not necessarily the right thing, it's just a better thing than that, right? In the sense that at least this one at least handles potentially infinite concept classes. Like the VC dimension of a half space is 1. Right? The VC dimension of a half interval is 1. It's very small, right? So that D over here just becomes 1. Okay? But the point is, so for things like, but then how is VC dimension related to concept class size? Remember this? How is D related to size of C? Like for finite things.
Well, your hypotheses in the concept class are different to the extent that they can classify different sets.
Yep. So again, remember the VC dimension is the size of the largest shatterable set. The set is shattered if it can be classified in all possible ways, right? So, so if I say that the size of my shattered set is K, the size of my shattered set is K, that means that you have to be able to classify it in all 2 to the K possible ways. That means that you have to have 2 to the K different hypotheses, because they have to classify those things in 2 to the K possible ways. Well, obviously, if you have a finite number of hypotheses, you can't have K be too large because it grows exponentially in 2 to the K, right? I claim that as a consequence of this is D, for finite classes, D is less than or equal to log of the size of the concept class. Right? In other words, you can't shatter more than D things because you need to have 2 to the D hypotheses to do it. You've only got that many hypotheses, right? So the number of points that you can shatter is no more than the log of the size of the concept class. So in some sense, this really subsumes that. Over here, this was saying your complexity measure is natural log of the concept class. This thing is saying, yeah, pretty much, except it's really VC dimension, which is like the complexity, which is like the log of the size of the concept class for finite concept classes. But for infinite concept classes, you can have a non-trivial value of this. Because you can have a non-trivial value of VC dimension, even when you have an infinite class. Okay? Now, so this is better in some sense. This more or less subsumes that. These are off by log factors, but that's not so important for our purposes. minutes, you might turn around and say, well, maybe there's something even better, right? Maybe there's there's another complexity, the Rademacher complexity, the whatever complexity, who knows, which is even better than this complexity. And then the answer becomes there's lower bounds. And it turns out that you can show that there's lower bounds that involve these two dimensions. You can show that you must have at least d over epsilon log, d over epsilon plus 1 over epsilon. So basically, these are almost exact. Right? This is saying that for a simple, completely general algorithm, draw a sufficiently large amount of data, return anything which is consistent, that if your data was d over epsilon log 1 over epsilon log epsilon log over delta, it would pull them. This is saying is that I don't care what your algorithm is whatsoever. You must use d over epsilon plus 1 over epsilon log 1. And you'll notice that these two things are the same except for this log. But in particular, as a function of the complexity of the concept class, it's VC dimensions. It both gives you a lower bound and an upper bound in terms of the right way of measuring the complexity of the thing that you're trying to learn. And again, now because we have lower bounds too, you can see that in fact the right measure of how your data requirements change as a function of epsilon and delta really is 1 over epsilon, and then like log over delta, and maybe some log factors which are close. But you can prove this. I wish I could show you this actual proof, because this one is actually not so bad, but it's something I can't do in 2 minutes. But this is really like this. You can see a version of me sneak in at something like that. Okay, and now, and I do have 2 minutes, what I can do in 2 minutes is somebody asked who was the person that was flattering me in my PhD thesis? You, right? This is all well and good, okay, except all of this falls apart when you have this, right? All these algorithms, everything, it completely falls apart, okay? People worked very hard, not just me, others, to try to see, can we modify, PAC learning in some way to take into account noise, because this sort of stuff just falls apart when you have noise. And the answer is that you can. There's something called the SQ model, which is the statistical query model. Okay. And the statistical query model is sort of like a generalization of the PAC model, or a different variant of the PAC model. It essentially does the following thing. The problem with noise is that the PAC model, right, you make very hard decisions based upon individual examples. If you remember like how we were doing that knocking out variables, like if I had something which was mislabeled, I'd knock out a whole bunch of variables that I could never get back again, right? And so noise, this kills the algorithm. But it kills it because you're making very hard decisions based upon individual examples. The statistical query model, I'll need just 2 more minutes, my apologies, but I'm going to be late, essentially says, I'm not going to allow you to look at individual examples. You are going to be allowed, though, to ask statistics about examples. Like instead of saying, does this particular patient have the flu, I'll allow you to ask questions like, what fraction of the patients that had the flu had chills? Or what fraction of the patients who had a fever ended up having the flu? You can ask statistical questions, which I will answer, which I will in fact simulate in the presence of noise, but I'm not going to allow you to look at individual pieces of data. Okay? You can show 2 things. One, that virtually every PAC learning and just general learning algorithm that ever exists can actually be construed, or in the statistical query model, you can really show that they really just need to ask statistics about the data, not about individual data points. Second, you can show that you can learn these things in the presence of noise, and you can come up with lower bounds and upper bounds. And essentially, the way noise comes into play is, suppose you have it depends what kind of noise you're talking about. Let's suppose you have the most benign kind of noise we have, Bernoulli white noise. Your labels are just flipped incorrectly an 8 fraction of the time. Like, the person who's giving you the data just makes it 5% of the time, he just gives you the wrong data. Okay? If you have that, then basically you just multiply everything by a factor of 1 over 1 minus 2 take this whole expression, multiply by this, take that whole expression, multiply by this. And this is essentially tells you how much your data needs to go up in the presence of noise. Okay? And this has an interesting interpretation, right? As eta approaches a half, what happens to this? It goes to infinite, which of course makes sense, right? If your labels are basically, they flip a coin 50-50, they gave you the right label, you're basically getting pure noise, right? You can't learn from pure noise, right? Okay? When eta is 0, what happens to this? This goes away. This tells you exactly, as your noise rate gets closer and closer to a half, how your data needs change. And this is essentially the complexity of noise, at least that kind of noise, that random noise. And you can show all that stuff. So I think PAC Learning is cool. Yes. All right, that's it for today. Thanks.
I think he just like, oh, you like, okay, you'd be great spokesperson. I'm sure they were really fun.
You enjoyed that. See you guys.
Yeah, that piazza puzzle was hilarious. Dude, it was so bad.
Like when I first saw it, like when we first put it up, I like did it, right? But I was listening to, and I was like, I was like, right again.